Hey everyone, welcome to Learn with Longman, where we will unravel the mysteries of intermolecular forces. Join us as we tackle questions like those in senior secondary school. If you're loving this video, find related resources on my Teachers Pay Teachers website, link in the video description. Let's dive in and explore together. Intermolecular forces, what are they? Intermolecular forces are the attractive forces between molecules that hold them together, while intramolecular forces are the chemical bonds within a molecule that hold its atoms together. Let's step into the realm of carbon dioxide gas, which is composed of separate carbon dioxide molecules. In each molecule, carbon and oxygen atoms unite in an intricate dance of covalent bonds. These are intramolecular bonds. If we look between the molecules, we will also see that weaker forces delicately draw the carbon dioxide molecules closer together. These are intermolecular bonds, and though their strength pales in comparison to the mighty intramolecular bonds, they are supremely important in understanding the physical properties of carbon dioxide and other covalent molecules. Dipole-dipole forces, fascinating in their nature, arise between polar molecules due to the attraction between the positive end of one molecule and the negative end of another. Let's have a look at a sample of chloroform, CHCl3. This useful little organic compound, which is famous for its historical use as a knockout medication and still has uses as a laboratory solvent and synthesis intermediate, is a polar molecule. The chlorine-containing end has a partial negative charge, and the hydrogen-containing end has a partial positive charge. When a sample of these molecules are together, they will arrange so that the positive end of one molecule is nearby to the negative end of another. This produces dipole-dipole forces, or bonds. So these are the dipole-dipole force which hold the molecules together. All in all, dipole-dipole bonds are fairly strong intermolecular forces. Hydrogen bonding is a special type of dipole-dipole force. Hydrogen atoms, covalently bonded to a highly electronegative atom, oxygen, nitrogen or fluorine, form a dipole-dipole force with another electronegative atom within another molecule. This forms a stronger bond between molecules, and they play crucial roles in various biological and chemical processes. To illustrate, let's dive into the miraculous liquid which is water. Here the magic of hydrogen bonding unfolds. Within a water molecule, the electronegative atom greedily tugs at the electrons it shares with each hydrogen. It takes the lion's share of these, creating a tremendous polarity across the water molecule. The very large positive charge obtained by the hydrogen on one water molecule and the very large negative charge obtained by the oxygen on another are irresistibly attracted. They set up a supercharged kind of dipole-dipole interaction called a hydrogen bond. These hydrogen bonds are so strong it is as if the water molecules have joined hands with their neighbours, resulting in a network of intermolecular attractions. These spirited bonds form, break and reform in a continuous dance, lending water its remarkable cohesion, surface tension and high boiling point. Many other substances will form hydrogen bonds, such as ammonia and alcohols, just to name a few. Dispersion forces, also known as London forces, are the weakest type of intermolecular force. They occur in all molecules, but are most often noticeable in non-polar substances. They arise from the temporary fluctuations in electron distribution, resulting in temporary dipoles that induce attractions between neighbouring molecules. Let's examine this as it occurs in everyone's favourite light maker, neon gas. Despite their noble nature, these small little atoms experience momentary shifts in their electron clouds. This movement creates sections of the atom which are negatively charged and sections which are positively charged. These temporary dipoles then draw the electrons of the neighbouring atoms into a similar arrangement and set up a fleeting intermolecular force, the dispersion force. The electrons are lively and ever moving, so the temporary dipoles form and disappear, and so too does the dispersion force. This makes it weaker than the other intermolecular forces. Alright folks, it's time to shift gears and dive into some intriguing questions. Get ready to test your knowledge with these brain teasers, sourced from the incredible resource shown below. Yes, you guessed it, it's available on my Teachers Pay Teachers website. Whether you're an eager student or a dedicated teacher, this resource is packed with valuable insights that will make a difference. So don't forget to click that link in the video description and discover how it can help you ace those challenging questions. Trust me, you won't want to miss out on this educational gem. First question, draw a diagram to represent the strongest intermolecular force which exists between molecules in a sample of hydrogen chloride gas. It's worth 3 marks. What I'd like you to do is pause the video, complete your attempt at this diagram, and then unpause to see what the answers in my marking guide are. So I've put up the marking guide, and hopefully yours is looking fairly similar to this. We have 2 hydrogen chloride molecules, and I have assigned the partially positive charge to the hydrogen and the partially negative charge to the chlorine in each of the molecules. The reason for this is because the chlorine, being more electronegative, is going to create a greater portion of the shared electrons than the hydrogen, and as a result ends up with a partially negative charge. This produces a polar molecule, and the dipole-dipole force which is produced is the attraction between the negative chlorine on one molecule and the positive hydrogen on another molecule. So did you hit these points? You identified that dipole-dipole forces were the strongest acting force. You assigned correct partial charges to each of the atoms in the molecules, and you aligned the correct ends of the molecule in the dipole bond. Second question, draw hydrogen bonds which can form between molecules of methanol and water. Again, 3 marks. Pause the video and come back for the answer. Here's my diagram, and hopefully yours looks quite similar. We have the methanol here, which is the CH3OH, and I've drawn 2 water molecules around the methanol. The reason I've drawn 2 is because we're adding on a little bit of added information here, and we're talking about hydrogen bond donors and hydrogen bond acceptors. And in this diagram, at the top, the water is acting as a hydrogen bond donor. It's still a hydrogen bond which is occurring between the oxygen on the methanol, and the hydrogen on the water. But you can see that the water is the one which is providing that hydrogen for the hydrogen bond, and hence it's a hydrogen bond donor. In the other hydrogen bond which is occurring here, the water is only providing the oxygen involved in that hydrogen bond between it and methanol. So the water is acting as a hydrogen bond acceptor because it's accepting the hydrogen in that hydrogen bond from the methanol. So hopefully you've addressed these 3 points in the marking guide. You have the correct orientation of hydrogen and oxygen on different molecules in your hydrogen bond. You're representing the water acting as a hydrogen bond donor, and you're representing the water acting as a hydrogen bond acceptor. Even if you haven't used that language, you've identified that there's more than one way that a hydrogen bond can occur between these 2 molecules. Don't forget to hit that subscribe button and stay tuned for an exciting lineup of videos. But that's not all. Keep those eyes peeled for a treasure trove of incredible resources that will catapult your science journey to new heights.